what Earth looked like 1 year after the dinosaurs died. Smoke still curls above fractured landscapes, and ash-laden skies scatter a dim, ghostly light across continents stripped bare. 1 year after the dinosaurs' reign ended, Earth teeters between desolation and renewal. Oceans murky with chemical upheaval, rivers choked with debris, and forests reduced to skeletal remnants. Tiny survivors, mammals, birds, insects, and plants navigate this altered world, probing fragile refuges and claiming the niches left vacant by giants. In this pivotal moment, life is fragile, adaptive, and relentlessly inventive. Join us as we trace the first fragile threads of recovery, witnessing a planet poised between catastrophe and rebirth. The world that wouldn't wake. Shadows clung to the planet with a persistence that defied the turning of the earth, creating a muted daylight that resembled the final moments of an endless dusk. In the atmosphere above, a dense shroud of sulfate aerosols estimated by climate models to have reached concentrations exceeding 100 teragrams scattered sunlight into a thin, silver haze that bleached colour from every landscape it touched. The initial firestorm produced by the Chicxulub impact had lofted soot high into the stratosphere, and a year later those grains remained suspended far longer than volcanic ash ever would, prolonging a dimness that cooled global temperatures by as much as 10 to 15 degrees Celsius across many regions. Beneath this leaden sky, photosynthesis limped forward at a fraction of its former efficiency, creating a world where even the most resilient plants struggled to hold their ground against a climate that had forgotten how to warm. Across what had once been vibrant, Cretaceous coastlines, wind carried fine layers of iridium-rich dust material that fell back to Earth after being blasted into orbit by the impact, forming thin veneers, detectable today in sediment cores from Denmark to New Zealand. Each grain of this extraterrestrial metal served as a testament to the violence that had reshaped the atmosphere, while the particles themselves contributed to the optical thickness that trapped the planet in a perpetual twilight. Radiocarbon and oxygen isotope measurements, extracted from early Paleocene proxies, describe a world where surface temperatures remained far below the seasonal norms of the preceding era, with prolonged cooling events documented in both marine and terrestrial deposits. These data help reconstruct the chilling reality that enveloped Earth 1 year after the dinosaurs' reign abruptly ended. Far inland, lowland floodplains that once supported a labyrinth of broad-leaved angiosperms now lie coated in layers of soot and pulverized quartz known as shocked minerals, their microscopic lamellae revealing the instant of catastrophic pressure they endured. This mineralogical fingerprint appears consistently across the KPG boundary, marking the global scale of the event that placed Earth into its long slumber. Even after 12 months, the surface still bore signs of the thermal pulse and megatsunamis that followed the impact, with geologists identifying chaotic sedimentary deposits known as event beds extending hundreds of kilometers inland from ancient coastlines. The persistence of these layers suggested that environmental stabilization had barely begun, and that erosion, deposition, and ecological recovery were all proceeding at glacial speed under the shrouded sky. Farther north, regions that once supported temperate forests now resembled barren steppes, with pollen records showing a dramatic decline in plant diversity attributed to prolonged light suppression. Analyses of fossilized plant cuticles from this period reveal weakened stomatal development, an adaptation to drastically reduced sunlight and disrupted carbon dioxide cycles. Even shade-tolerant species, such as certain ferns and understory magnoliids, showed signs of metabolic stress in the microscopic scars left on their leaf surfaces. These details provide tangible evidence of the struggle that vegetation faced in an atmosphere starved of the photons necessary to rebuild biomass. With each passing week, decomposition outpaced photosynthesis, and ecosystems that had once thrived with towering fauna found themselves collapsing into nutrient-poor wastelands. In the oceans, where surface waters normally teemed with planktonic life, microfossil assemblages tell a story of collapse that paralleled the gloom above. Planktic foraminifera, tiny carbonate-shelled organisms that recorded chemical conditions in their shells, experienced near-total extinction at the boundary, and even a year later, the surviving species displayed severely reduced abundances. Geochemical signatures from deep-sea cores indicate that primary productivity remained suppressed for months, with carbon isotope excursions reflecting the stalling of the marine carbon pump. The drop in light penetration caused by stratospheric aerosols hindered the recovery of photosynthetic plankton, resulting in diminished oxygenation of surface waters and contributing to regional hypoxia. This cascade of effects confirmed that the oceans, like the land, were ensnared in a prolonged and suffocating lethargy. On continental interiors, the animals that survived did so by retreating into ecological corners that offered a semblance of stability. Small mammals, such as early eutherians and multituberculates, relied on nocturnal or crepuscular behaviors that served them well in an environment where strong daylight was nearly absent. Evidence from tooth microwear suggests that many of these mammals adapted by broadening their diets, shifting toward detritus, carrion, and whatever plant material persisted beneath the gloom. Birds belonging to the clades that survived the extinction, particularly those with ground-dwelling habits or robust beaks capable of processing seeds, exploited the diminishing but critical seed banks left by dying flora. These behavioral and anatomical traits offer insight into why some lineages weathered the twilight, while others vanished forever. In the polar regions, where seasonal darkness was a familiar challenge, Earth's dimming created conditions even harsher than prehistoric night. Ice core analogues and paleoclimate simulations suggest that sea ice expanded dramatically during this period, with winter-like temperatures pushing into lower latitudes and altering atmospheric circulation patterns. The steepened temperature gradients between equatorial and polar regions intensified certain wind systems while weakening others, creating unstable weather that thwarted the slow crawl toward ecological stabilization. Geological evidence from early Paleocene deposits indicates increased storm activity, more frequent temperature oscillations, and shifts in precipitation that further hindered the planet's ability to regain equilibrium. Even microbial communities registered the planet's paralysis, as evidenced by biomarkers preserved within sedimentary rocks that signal disruptions to sulfur and nitrogen cycles. The layers deposited during the first year show altered ratios of sulfur isotopes, suggesting that bacterial sulfate reduction intensified in anoxic environments created by widespread surface die-offs. Similarly, nitrogen-fixing microbes struggled under reduced plant biomass and limited sunlight, causing nutrient imbalances that echoed through food webs. These microbial signals reveal how deeply the darkness infiltrated the planet's biological machinery, affecting organisms that had endured mass extinctions before but now faced one of unprecedented scale. Everywhere across Earth, the evidence converged on a singular truth. The planet existed in a state of suspended animation, neither fully dying nor truly beginning to heal. The atmosphere's veil of aerosols, the geological scars imprinted across continents, the faltering pulse of plant and marine productivity, and the tenuous survival of small, adaptable creatures together formed a portrait of a world caught between eras. As the dim sky held its grip on the land, a silence settled into the once vibrant forests that lingered beneath the haze, urging us to descend from this panoramic stillness into the shadowed remains of ancient woodlands where the true depth of collapse awaited, waiting in tangled ruins for the faint stirrings of eventual renewal. Forests without footsteps. Dim light filters through the fractured remnants of towering trees, revealing a landscape frozen between decay and stillness. A year after the Chicxulub impact, the forests retained the skeletal outlines of their former grandeur. Yet, the muted illumination from lingering aerosols rendered the canopy a grey lattice of broken branches. Sediment cores taken from these woodland sites show that ash layers remained thickly deposited on the soil surface, inhibiting nutrient cycling and suppressing new growth. The reduced solar radiation slowed photosynthesis, with leaf tissue analysis indicating chlorophyll levels far below those of pre-extinction flora. This half-light, combined with cooler temperatures estimated at 10–15 degrees Celsius below Cretaceous norms, set the stage for a woodland that existed in stasis, neither thriving nor fully decaying. Fungal networks crawl along fallen logs, their intricate threads slowly reclaiming what was blasted into silence. Paleomycological evidence from early Paleocene deposits indicates a massive bloom of saprotrophic fungi in the first year after impact, exploiting the sudden abundance of dead conifers and angiosperm debris. Microscopic examinations of hyphal patterns reveal rapid colonization of lignin-rich wood, with some species capable of breaking down structural polymers even under limited light and low temperatures. The proliferation of these fungi created dense mats on forest floors, accelerating localized decomposition while simultaneously forming the first scaffolding for a new ecological succession. Delicate spores drift through the thickened air, marking the tentative rise of plant species that endure despite shadows and chill. Palynological studies reveal a dominance of ferns, lycophytes, and select gymnosperms, collectively forming the well-documented fern spike that characterizes the immediate post-extinction interval. Surviving angiosperm lineages were often small, understory-adapted plants, capable of low-light photosynthesis and rapid colonization of cleared patches. Analyses of cuticle morphology indicate that many species exhibited narrow leaves and thicker epidermal layers, adaptations to conserve water and endure cooler, drier microclimates beneath the aerosol-filtered sky. Beneath shattered branches, hollowed trunks hold only the faintest traces of creatures that once moved in abundance. Fossil evidence indicates that canopy-dwelling birds largely disappeared, leaving ground-foraging survivors as the primary avian lineages in these woodlands. Tiny mammals, early eutherians and multituberculates occupied niches among leaf litter and fallen logs, scavenging detritus or preying on surviving insects. Comparisons of tooth microweir showed diet broadening, including seeds, fungi, and decaying plant matter, a survival strategy necessitated by the collapse of more specialized food webs. Needle-strewn floors lie thick and undisturbed, preserving the imprint of a vanished world beneath their cold weight. Measurements of litter layer thickness from sediment cores suggest accumulation rates far higher than typical modern forests, a consequence of slowed decomposition in cooler, darker conditions. Analyses of lignin and cellulose breakdown reveal that microbial metabolism lagged months behind deposition, leaving dense mats of half-decayed material across broad forest patches. These mats created microhabitats for surviving invertebrates and mammals, even as the absence of abundant insects limited the diversity of these communities. Edges of the woodland reveal accumulations of ash and particulate matter, reshaping the very soil that supports life. Geochemical analyses show altered pH, and elevated concentrations of sulfur and trace metals from impact-derived fallout. These chemical changes suppressed nitrogen-fixing microbes and slowed recovery of plant-available nutrients, particularly in the upper 10 centimeters of soil. As a result, root systems grew more shallow and less dense, leaving trees and shrubs vulnerable to wind and erosion, a fragility reflected in widespread evidence of slope slumping in early Paleocene landscapes. Within the cracked bark of ancient conifers, decomposers exploit every fiber, leaving intricate patterns of collapse. Observations of fossilized wood reveal longitudinal channels formed by early colonizing fungi and detritivorous arthropods, though their frequency is markedly lower than in pre-extinction forests. This pattern demonstrates both the abundance of decaying material and the scarcity of specialized decomposers, a signature of a simplified, stressed ecosystem. In combination with slowed lignin breakdown, these factors created persistent woody debris that would feed future ecological succession once light levels and nutrient cycles gradually improved. Sunlight, filtered through distant haze, barely reaches the understory, creating pockets where only the hardiest plants survive. Surviving flora include shade-tolerant ferns, early monocots, and hardy gymnosperms that could photosynthesize at minimal irradiance. Growth rings from fossilized wood show narrow annual bands, indicating slow growth rates, while frost, scars, and other damage mark continued stress from both cold snaps and episodic drought. These micro-environmental pressures shaped the selective survival of plant species and set the stage for post-extinction vegetation dynamics. Exposed roots twist over unstable earth, evidence of the forest's slow surrender to erosion and gravity. Paleosol studies show that root networks were frequently undermined by ash-laden runoff and slope failures, depositing fine sediment into the first-generation floodplains. This geomorphic instability contributed to local microhabitat destruction, but also created pockets where seeds and spores could accumulate, preparing the groundwork for eventual recolonization. The uneven terrain became a mosaic of death and potential, illustrating how abiotic forces reshaped the structure of the surviving forests. Traces of former animal activity are faint, scattered, and almost erased, hinting at the creatures that survived the catastrophe. Fossil trackways and burrows from small mammals suggest highly localized activity in shaded, debris-filled areas, while avian and reptilian traces are extremely rare. The scarcity of large herbivores is reflected in limited browse marks and minimal trampling of the litter, signaling a profound collapse of the Cretaceous trophic pyramid. Even within this ecological vacuum, opportunistic species exploited niches, slowly filling spaces that would eventually form the foundation of Paleocene ecosystems. Streams winding through this hollowed forest carry sediment and debris, charting the slow remolding of the land. Stratigraphic records from channels show ash-rich deposits mixed with woody debris, evidence of repeated erosional pulses following treefall and slope destabilization. Oxygen isotope ratios in these sediments indicate cooler water temperatures, while grain size analyses document the transport of fine organic matter from decaying forests into fluvial systems. These waterways became both conduits of destruction and vectors for new life, redistributing nutrients and organic material across the fragmented landscape. From the silent depths of decaying woodlands, a subtle current of change begins, guiding the eye toward waterways reshaped by ash and geomorphic upheaval. Despite the apparent stillness, decomposition, erosion, and slow colonization are quietly rewriting the forest architecture, preparing a template for new ecosystems to emerge. The skeletal remains of fallen trees, the sparse activity of surviving fauna, and the microbial processes hidden in litter and soil all hint at the persistent, if muted, pulse of life beneath the gloom. As these hollowed woodlands yield to gravity and flowing water, the scene naturally draws attention to the next phase of transformation. Rivers and floodplains absorbing the detritus of collapse, carrying the promise of renewal downstream. Rivers running black, winding through the hollowed forest, streams gather momentum, pulling charcoal, ash, and fallen wood into restless ribbons of water. The remnants of decaying woodlands feed these nascent waterways, and each rivulet carries not only organic debris, but also the chemical echoes of the Chicxulub impact. Sediment cores from early Paleocene channels reveal layers rich in iridium and shock-melted minerals mingled with fine ash particles. The water's surface, darkened by suspended detritus, reflects a pale sky filtered through lingering aerosols, while temperature reconstructions suggest rivers remained 10–15 degrees Celsius cooler than pre-impact norms. Even in this dim flow, the energy of erosion reshapes the land, carving temporary channels and reworking the forested terrain into a patchwork of unstable floodplains. Beneath low-hanging clouds of smoke and lingering haze, sediment churns in turbulent eddies, recording the violent legacy of wildfire and impact. Geomorphologists studying modern analogues estimate that post-catastrophe rivers experienced pulses of flow many times higher than their pre-extinction baselines, driven by deforested slopes and ash-saturated soils. Pebbles, uprooted logs, and fine silts tumble downstream together, forming sedimentary strata that preserve a timeline of cascading ecological collapse. Analysis of grain size and mineral composition shows episodic surges corresponding to early tropical storms or monsoon-like precipitation, illustrating how post-impact hydrology amplified the destructive energy of these rivers. At the earliest curves of the stream, uprooted trees and boulders form temporary dams, diverting water and concentrating mineral-rich debris. These obstructions create localized pools that trap spores, pollen, and charcoal, effectively storing a record of both devastation and potential regeneration. Field observations and sedimentary evidence indicate that these isolated eddies supported surviving vertebrates and invertebrates, offering temporary refuges in an otherwise hostile landscape. Burrows of small mammals are occasionally preserved beneath compacted ash deposits, providing a glimpse into the first attempts at recolonization along riparian corridors. Fine particulate matter darkens the flow, carrying chemical signatures of sulfur, iridium, and shock-melted minerals toward downstream plains. Geochemical analyses reveal that these rivers acted as conveyor belts for elements redistributed from impact ejecta, including elevated concentrations of platinum group metals. Phosphorus and nitrogen, carried in suspended sediments, reflect the altered nutrient cycles caused by ashfall and massive plant die-offs. These chemical pulses, moving steadily toward the coasts, hint at a landscape-wide feedback between erosion, decomposition, and early aquatic colonization, effectively linking terrestrial devastation to marine consequences. In shallow floodplain channels, surviving vegetation clings to banks, its roots slowly anchoring sediment, even as torrents strip the surrounding soils. Palynological studies from these margins show concentrations of hardy fern spores, early angiosperms, and gymnosperms, suggesting that riverside plants were among the first to persist in the post-extinction environment. These vegetated corridors acted as stabilizers, reducing erosion in some areas while leaving others exposed, creating a complex mosaic of stability and vulnerability along the water's path. Charcoal fragments from burned forests float alongside delicate spores, marking both destruction and the seeds of renewal carried in the current. Radiocarbon and geochemical dating indicate that pulses of charcoal coincide with periods of intense wildfire immediately following the impact, producing high-energy sediment-laden flows. Palynological data reveal that some spores survived transport without damage, suggesting rivers functioned as dispersal highways for resilient species, slowly seeding downstream floodplains with the genetic material necessary for eventual ecosystem recovery. Water temperature readings inferred from oxygen isotopes reveal persistently cooler conditions, reflecting continued atmospheric opacity and diminished solar input. Analysis of sediment cores confirms that rivers remained significantly colder than modern analogues in similar latitudes, and dissolved oxygen levels indicate slow microbial metabolism within the water column. Such conditions not only suppressed primary productivity, but also influenced the distribution of surviving aquatic invertebrates, which were constrained to the shallow margins where sunlight and warmth were slightly greater. In braided sections, sediment layering captures pulses of ash and detritus, creating geologic records of each erosional surge. Stratigraphic sequences demonstrate alternating layers of fine silt, coarse sand, and organic debris, documenting episodic surges from slope failure, forest collapse, or storm-driven floods. These patterns illustrate the dynamic, high-energy environment of post-extinction rivers and provide insight into the geomorphic processes shaping valleys and floodplains. Each layer preserves a subtle chemical signature, a frozen map of a world still recovering from planetary trauma. Alongside channels, early mammals and birds exploit isolated pools, their fleeting presence recorded in trace fossils and burrow impressions. Tiny vertebrates, navigating between sediment-laden flows and vegetated margins, left subtle tracks and gnaw marks preserved under ash and silt deposits. Fossil evidence shows opportunistic feeding on both plant detritus and invertebrates washed into the streams, underscoring how the rivers themselves became lifelines for surviving species. The juxtaposition of energy-driven sediment transport and localized refuge highlights the dual role of rivers as agents of both destruction and survival. Floodplains swell with mud and woody debris, reshaping valley floors with each seasonal or storm-driven surge. Geophysical modeling indicates that these post-impact floodplains were far broader and more unstable than their Cretaceous predecessors, constantly reorganized by episodic floods and sediment-laden flows. Woody, debris jams, and ephemeral levees created temporary habitats for plants and animals, while simultaneously feeding turbidity flows that transported nutrients and minerals toward downstream estuaries. These pulses established the first conditions for riparian succession and hinted at the slow re-establishment of ecological networks along river corridors. Near the river mouths, chemical analyses detect elevated trace metals and nutrients, a concentrated memory of the global catastrophe upstream. Elements such as iridium, chromium, and phosphorus are measurably higher in estuarine sediments, offering a fingerprint of impact-derived fallout transported hundreds of kilometers from the interior. These rivers not only delivered sediment and organic matter, but also carried geochemical markers that would influence coastal ecosystems, potentially triggering shifts in primary productivity and early food webs in nearshore waters. As the darkened waters flow into the coastal margins, the rivers deliver both sediment and chemical signals that hint at transformations waiting to unfold in the oceans beyond. Despite the turbulence, patterns emerge: concentrated channels, sediment plumes, and chemically enriched deposits revealing the enduring link between terrestrial collapse and marine response. The river's journeys capture the first moments of a planetary system recalibrating, carrying the memory of wildfire, erosion, and chemical upheaval toward the seas. In these darkened currents, we glimpse the next stage of post-impact recovery. Oceans shaped not only by the direct effects of the asteroid, but also by the cumulative material and energy delivered from the reshaped land. Seas of ghosts. Where rivers once surrendered their burden, the coastal waters churn with ash, silt, and chemical traces of a planet in upheaval. The input from sediment-laden rivers combines with lingering impact fallout, forming a thickened, muted ocean surface that reflects a sky still dimmed by atmospheric aerosols. Sediment cores, collected from early Paleocene shorelines, reveal enriched layers of iridium, sulfur, and ash, marking the confluence of terrestrial destruction and oceanic response. Light penetration is severely reduced, and planktonic productivity drops sharply, creating a ghostly expanse where sunlight struggles to reach beneath the surface. Even in shallow waters, chemical imbalances hint at the fragility of life and the profound challenges facing post-impact marine ecosystems. Just below the mirror-like surface, planktonic life flickers briefly, struggling in water thickened by suspended sediment and nutrients. Fossilized microplankton from this interval reveal drastic reductions in species diversity, with some previously dominant calcareous nanoplankton nearly disappearing. Oxygen isotope analysis of their preserved shells indicates cooler surface temperatures, yet frequent hypoxic conditions prevented sustained population growth. These tiny organisms, foundational to the marine food web, struggled to reproduce, creating cascading effects for higher trophic levels, including fish, cephalopods, and early marine reptiles. Toxic algal blooms swell, coloring shallow seas in muted greens and browns, a visual echo of terrestrial devastation. Palynological evidence suggests opportunistic phytoplankton thrived in nutrient-rich runoff zones, creating massive blooms that quickly depleted dissolved oxygen. Chemical analyses indicate spikes in nitrogen and phosphorus, derived from both rivers and decaying forest biomass, which fueled these blooms. While visually striking, these surges were catastrophic for most other marine life, driving widespread hypoxia and contributing to mass mortality events in coastal ecosystems. Dissolved oxygen plummets in midwater layers, creating vast zones inhospitable to most marine animals. Geochemical profiling of sediment traps shows persistent oxygen minimum zones extending tens of meters below the surface, suffocating midwater plankton and disrupting vertical migration patterns. Fish and small invertebrates either perished or retreated to the remaining oxygenated pockets, leaving ghostly voids in previously productive habitats. This anoxic layering reflects the lasting influence of impact-generated aerosols, ash deposition, and riverine nutrient influx, combining to produce a chemically stratified and unstable water column. Fish populations collapse, their skeletal remains drifting silently toward the ocean floor, marking the first wave of marine mortality. Early Paleocene fossil assemblages from coastal deposits reveal mass mortality layers dominated by small teleosts and ammonites, often interspersed with bivalve shells. Taphonomic evidence shows rapid burial by fine sediments, preserving delicate structures while also reflecting episodic surges of erosion and deposition. These die-offs illustrate the rapid breakdown of complex marine food webs, leaving oceans largely empty and eerily quiet compared to their Cretaceous vitality. Sediment cores reveal layers enriched with iridium and sulfur, a chemical signature of both impact and riverine influx. High-resolution geochemical mapping shows that coastal basins functioned as collectors of material transported from the continents, concentrating trace metals and nutrients that fueled localized biogeochemical feedbacks. Elevated sulfur levels indicate both the deposition of impact-derived aerosols and early post-impact microbial activity in anaerobic environments. These chemical reservoirs shaped the composition of surviving plankton and microbial communities, laying the foundation for eventual recolonization in downstream ecosystems. In isolated pockets, hardy microbes and extremophile plankton survive, exploiting niches too toxic for larger organisms. Studies of microfossil assemblages suggest certain cyanobacteria and green algae adapted to low light, high nutrient, and hypoxic conditions, thriving where most organisms could not. Their metabolic activity contributed to biogeochemical cycling, slowly transforming water chemistry even under extreme stress. These survivors represent the first glimmers of ecological recovery in an otherwise desolate marine environment, demonstrating resilience rooted in adaptability rather than size or strength. Currents carry debris and nutrients into deep basins, where oxygen depletion and chemical imbalance intensify. Stratigraphic analysis shows thick accumulations of organic matter settling in deeper waters, creating anoxic muds that preserve both microfossils and chemical signatures. These deep deposits serve as historical records of post-impact ocean stress, showing how rivers and surface processes directly influenced seafloor chemistry. Even as oxygen-deprived basins expanded, currents redistributed nutrients and particulates, creating gradients of survival and collapse across marine landscapes. Surface waters, warmed intermittently by sunlight filtering through lingering haze, support fleeting growth spurts of opportunistic algae. Thin photic zones become hotspots of ephemeral productivity, where small herbivorous zooplankton occasionally find sustenance. However, these bursts are short-lived, constrained by oxygen depletion below and ongoing sedimentation from rivers above. The interplay between episodic growth and persistent chemical stress underscores the fragile balance of early Paleocene coastal ecosystems and the tenuous foothold for surviving life. Carcasses of ammonites, bivalves, and small fish punctuate the ghostly seascape, evidence of an ecosystem in freefall. Fossil beds show overlapping mortality events, capturing the rhythm of ongoing environmental stress. Ash deposition, hypoxia, and temperature fluctuations repeatedly strike these early survivors. The visual and chemical imprint of this die-off paints a haunting portrait of an ocean in transition, with life reduced to scattered, struggling pockets, awaiting the slow recalibration of biogeochemical cycles. Chemical analyses show spikes in trace metals, nitrogen, and phosphorus, linking terrestrial upheaval to marine disruption. Coastal waters act as a junction where rivers, ashfall, and decomposing terrestrial matter converge, delivering both destruction and potential resources for resilient species. These nutrient and metal pulses create localized microenvironments, some too toxic for most life, yet others offering niches for opportunistic colonizers. The ocean, though largely empty, contains the seeds of its future, hidden in these chemically complex margins. Amid the collapse of the seas, a few resilient organisms cling to existence, hinting at the evolutionary paths that will shape future oceans. Microbial mats, extremophile plankton, and opportunistic fish navigate a chemically volatile world, exploiting the gaps left by mass mortality. The ocean's surface, midwater layers, and benthic zones each tell a story of collapse, interwoven with potential, a delicate balance between destruction and persistence. Within these fragile niches, life's persistence is measured not by strength, but by adaptability and the relentless exploitation of opportunity, a quiet prelude to the small mammals, birds, and reptiles that will inherit the reshaped earth. Creatures of the margins. In the shadow of fallen forests, tiny mammals emerge from burrows, nose twitching as they seek the scraps left behind. Paleocene multituberculates, roughly the size of modern rats, scavenge seeds, insects, and carrion, their nimble limbs allowing them to exploit narrow fissures in ash-laden soil. Fossilized burrows from this period indicate complex tunnel systems, some extending several meters beneath fallen conifers, providing protection from predators and insulating against lingering cold. Even in these marginal habitats, survival is a careful negotiation between energy intake and exposure, with each movement a measured risk in a world still dominated by the debris of catastrophe. Underneath the shadowed foliage, insects scuttle along decaying logs, turning detritus into sustenance in a silent world. Fossilized beetle fragments and traces of early ants suggest rapid colonization of fallen wood, leaf litter, and sap-rich bark. These arthropods not only recycle nutrients, but also sustain small vertebrates that depend on them for protein. Observations from similar modern analogues indicate that insect populations could surge in nutrient-rich microenvironments, providing a fleeting abundance of resources that punctuate the constant struggle for survival. Birds, small and wary, hop cautiously from branch to branch, feeding on seeds scattered by collapsed vegetation. Early Paleocene avians, resembling diminutive perching forms, exploited gaps in the canopy created by toppled conifers. Their sharp beaks and acutely developed vision allowed precise foraging even under dim light filtered through lingering atmospheric haze. Pollen analysis suggests that some flowering plants persisted in these pockets, providing a vital food source that shaped the early post-extinction avian ecology. Reptiles bask intermittently on exposed rocks, exploiting warmth during fleeting sunlit hours while remaining hidden from predators. Lizards and small crocodiliforms likely used microclimates along streams or open patches where solar radiation briefly penetrated the dense atmospheric veil. Fossil trackways and bone fragments reveal that these reptiles were opportunistic feeders, consuming insects, carrion, and even small vertebrates, their survival hinging on patience and adaptability rather than size or aggression. These creatures, though small, play a crucial role in sustaining the nascent terrestrial food web. Opportunistic feeders scavenge the remains of larger creatures, their sharp senses detecting even the faintest odours of decay. Evidence from coprolites and gnaw marks indicates that mammals and birds scavenged both terrestrial and aquatic carcasses, bridging ecosystems and transporting nutrients across fragmented landscapes. Such behaviour allowed these marginal survivors to exploit niches abandoned by extinct giants, effectively turning collapse into opportunity. The ecological principle is clear. Survival favoured those able to act swiftly and adaptively, leveraging what the larger, slower creatures once dominated. Nestlings cling to the remains of broken branches, relying on parental vigilance and the scattered safety of a hollowed ecosystem. Fossilized nests and juvenile bones suggest that reproductive strategies emphasized concealment and rapid development, minimizing vulnerability in an unstable environment. Parents often used fallen logs or rock crevices as protection, balancing proximity to food with predator avoidance. These reproductive behaviors reflect both ecological necessity and the subtle emergence of evolutionary traits that would shape mammals and birds for millions of years to come. Tracks and burrows etched into ash-laden soil reveal movement patterns of mammals and reptiles adapting to unpredictable terrain. Paleontologists have documented complex networks of paths radiating from central refuges, indicating repeated foraging and escape strategies. Such behavioral evidence underscores the importance of landscape memory. Survivors learn to navigate hazards, avoid exposure, and exploit microhabitats, creating an early framework for ecological resilience in a world still marked by instability. Microhabitats, pools of water, fallen logs, and mossy patches become critical refuges for survival in this fragile landscape. These small pockets buffer temperature extremes, shelter against predators, and concentrate scarce food resources. Fossil evidence, including preserved pollen and spore concentrations, shows that even minor variations in terrain or plant debris could define survival. Life clings to these margins, illustrating how microtopography and ecological heterogeneity shape recovery in the immediate post-extinction interval. Early mammals display dietary flexibility, switching between seeds, insects, and carrion depending on availability. Dental morphology and microwear analyses reveal omnivorous tendencies, with some species capable of digesting tough plant material or opportunistically feeding on smaller animals. This adaptability contrasts sharply with the specialization of extinct dinosaurs, highlighting how ecological generalists gained a foothold in post-catastrophe ecosystems. Survival is contingent on versatility, a trait that allowed these creatures to navigate both environmental unpredictability and interspecies competition. Insects flourish briefly in nutrient-rich microenvironments, contributing to decomposition and sustaining small vertebrates. Beetles, ants, and other detritivores process decaying organic matter, cycling nutrients back into the soil and supporting higher trophic levels. Fossilized frass and burrowed wood indicate that these arthropods were prolific, their activity driving the subtle reconstruction of forest floor ecosystems. They form an invisible network, vital to the persistence of marginal survivors and the slow regeneration of early Paleocene forests. Interactions between species are fleeting and cautious, balancing the risk of predation against the necessity of foraging. Evidence of small carnivorous mammals hunting insects or scavenging carrion alongside herbivorous competitors suggests a delicate equilibrium. These early communities exemplify a behavioral choreography dictated by scarcity, spatial constraints, and environmental stress, revealing survival strategies that prioritize opportunity, timing, and agility over raw strength. Even among these marginal survivors, life is constrained by temperature, daylight, and the lingering cold that grips the mid-latitudes. Isotopic analyses indicate that average annual temperatures remain depressed. Sunlight penetration was reduced by lingering aerosols, and growing seasons were truncated. The combination of cold, dim light, and fragmented food availability defines the limits of survival, underscoring the tenuousness of life on the post-impact Earth. Yet within these constraints, mammals, birds, reptiles, and insects persist, quietly shaping the ecosystems that will gradually expand and diversify, adapting to climatic pressures and seeking shelter and sustenance wherever the harsh landscape allows. A winter that outstayed its welcome. The sun, veiled behind a haze of fine aerosols, casts a dim, cold light over forests and plains alike, leaving landscapes muted and silent. Fossil evidence from early Paleocene sediments shows reduced plant growth and stunted trees across mid-latitude regions, while isotopic analyses of oxygen and carbon reveal sustained surface cooling up to several degrees Celsius below pre-impact averages. With sunlight filtered and scattered by the lingering atmospheric dust, primary productivity faltered, creating cascading effects that limited food availability for both herbivorous and omnivorous survivors. Even areas that previously supported robust Cretaceous ecosystems were transformed into subdued, shadowed expanses, emphasizing the slow, persistent grip of global cold on life. Ice crystals form in early mornings, clinging to fallen leaves and burrow entrances, marking a world gripped by a relentless chill. Paleobotanical records suggest that frost extended into zones previously temperate, killing seedlings and constraining the regeneration of angiosperms and conifers alike. Burrow-dwelling mammals became increasingly reliant on insulated microhabitats to avoid freezing, often remaining below ground for extended periods. Observed skeletal adaptations in small vertebrates hint at energy conservation strategies, including torpor-like behaviors, reduced activity, and clustering in sheltered spaces to withstand the prolonged cold. Temperature reconstructions from oxygen isotopes reveal drops of several degrees Celsius across continents, persisting far beyond initial estimates of an impact winter. Sediment cores indicate that thermal stress lasted not months, but over an entire year, with abrupt seasonal changes muted by persistent haze. These sustained low temperatures slowed metabolic rates in surviving warm-blooded species, forcing shifts in feeding patterns and territorial behavior. Even rivers and shallow wetlands, once abundant with food, froze or became inhospitable during peak cold, further challenging survival. Growing seasons contract, limiting the availability of seeds, fruits, and foliage for small mammals and birds alike. Fossilized plant remains indicate delayed budding and fruiting, which in turn constrained food for foraging vertebrates. Birds adjusted by extending their diets to include insects, fungi, and scavenged carcasses, while mammals became increasingly omnivorous, exploiting carrion and stored plant material. The disruption of these seasonal rhythms created a precarious balance, where misjudged timing could mean starvation or reproductive failure. Migration patterns are disrupted as the usual cues of daylight and temperature fail, leaving some species stranded in inhospitable zones. Early Paleocene birds and small mammals lacked the predictability of seasonal light and warmth, causing many to attempt movement under suboptimal conditions. Isotopic evidence from fossil feathers and bone collagen suggests delayed or incomplete migratory behavior, with some individuals trapped in nutrient-poor regions. The breakdown of established migratory circuits compounded the stresses already imposed by limited food and harsh temperatures. Reproductive cycles slow or halt entirely, evidenced by fossilized nests with aborted clutches and juvenile remains in seasonal layers. Nesting data from small mammals and birds indicate shortened breeding windows and reduced clutch sizes, reflecting both environmental stress and resource scarcity. Insects, too, experience developmental delays, with prolonged larval stages recorded in amber and sedimentary deposits. The synchronization of reproductive events with ephemeral resource availability became a high-stakes gamble in a world where timing dictated survival. Even insects experience slowed development, with extended larval stages and delayed emergence further constraining food availability. Fossilized pupae and larval cases reveal that many species paused development until conditions improved, creating temporal bottlenecks in nutrient cycling. These delays affected not only the insects themselves, but also the small vertebrates that relied upon them for sustenance. The cascading effects of slowed invertebrate life illustrate the delicate interdependence of early post-impact ecosystems and the profound influence of persistent climatic stress. Snow and frost accumulate in atypical latitudes, reshaping riverbanks, sheltering microhabitats, and modifying terrain traversable by survivors. Sedimentological evidence indicates episodic deposition of frost-heaved soils and ice lenses, which altered burrow integrity and foraging pathways. Small mammals, reptiles, and birds adapted by relocating or deepening shelters, while insects and amphibians sought insulated microenvironments beneath logs or leaf litter. These microclimatic refuges became essential nodes of survival, allowing life to persist in pockets even as the broader landscape remained inhospitable. Forest floor temperatures dropped below thresholds critical for small reptiles, forcing shifts in activity patterns and habitat selection. Fossilized lizard and crocodiliform remains suggest extended dormancy periods and behavioral adjustments, such as sunbasking only during brief intervals of favorable radiation. Predatory behaviors slowed, feeding rates decreased, and opportunistic scavenging became more common. These adaptations illustrate the delicate balance between metabolic needs and environmental limits, reinforcing that survival depended not on size or strength, but on flexibility and patience. The combination of diminished sunlight and persistent cold creates a silent, frozen landscape, punctuated only by the cautious stirrings of surviving mammals and birds. Coprolites and trackways indicate that many species concentrated near water sources and sheltered microhabitats, minimizing exposure to harsh conditions. Even with limited movement, energy expenditure was tightly rationed, and ecological interactions became subtle and deliberate. Life continued, but only in measured, almost imperceptible rhythms, echoing the broader planetary inertia. Physiological stress indicators in fossils suggest energy conservation strategies. Huddling, burrowing, and opportunistic feeding become essential to survival. The repeated layering of frost and snow, combined with sparse food resources, selected for behaviors and morphologies that would have long-term evolutionary implications. Individuals that could endure prolonged scarcity, tolerate low temperatures, and exploit marginal niches persisted, providing the seed population for eventual ecosystem recovery. Survival was less about dominance and more about adaptability under relentless environmental pressure. Beyond the cold, life persists in refuges, burrows, nests, and sheltered crevices, harboring the next generation of Earth's reclaimers. Fossil evidence demonstrates that even in the harshest mid-latitude climates, these microhabitats buffered organisms from extreme cold, provided access to residual food, and allowed reproduction to continue, albeit at a reduced pace. Within these hidden sanctuaries, mammals curled against each other, birds nested in insulated hollows, and insects paused within leaf litter, quietly maintaining the threads of ecological continuity. As the planet slowly released its grip of global chill, these refuges became crucibles of survival and innovation, nurturing species whose resilience and ingenuity would shape the contours of recovery across the emerging Paleocene landscapes. Beneath the ash and soil, snaking below layers of ash and soil, hidden tunnels wind through cooled sediment, shielding life from the harsh winter above. Fossilized burrows discovered in early Paleocene deposits indicate that mammals, small reptiles, and even insects exploited these subterranean refuges, finding protection from temperature extremes and diminished sunlight. Sediment analyses show that soil temperatures remained significantly warmer than the frozen surface, creating a narrow but reliable thermal buffer that allowed life to persist where above-ground conditions were deadly. In these shadowed networks, survival was a matter of patience, energy conservation, and careful navigation through cramped, interlacing tunnels. Mammals curl tightly in burrows, their small bodies conserving heat while waiting for fleeting periods of foraging opportunity. Fossil evidence suggests repeated use of the same tunnels across months, implying a level of behavioral sophistication and site fidelity previously underestimated for early post-impact species. Burrow walls were often reinforced with root systems or decayed wood, which provided both insulation and structural stability. These adaptations allowed small vertebrates to maintain homeostasis, reduce predation risk, and conserve the limited energy available during the harshest months of post-impact winter. Trace fossils reveal repeated movement through intricate underground networks, evidence of survival strategies honed in darkness. Footprints and burrow scratches indicate that some species maintained constant territorial patrols, while others adopted highly localized ranges centered around caches of seeds, fungi, or carcass remnants. The spatial complexity of these refuges suggests that survival depended not only on individual endurance, but also on an intimate understanding of subterranean topography. These hidden corridors became lifelines, silently connecting pockets of life in an otherwise frozen landscape. Root systems of fallen conifers provide structural reinforcement and microclimates, allowing nesting and storage of limited food supplies. Burrowing species exploited gaps between root masses to stabilize tunnels and create small chambers for nesting or hibernation. Fossilized remains of seeds and stored plant material in these chambers indicate that early Paleocene mammals engaged in strategic caching, buffering themselves against food scarcity. Even insects took advantage of these microclimates, developing sheltered pupation sites that would ensure emergence when environmental conditions allowed. Insects and arthropods exploit narrow crevices, sustaining themselves and indirectly supporting vertebrate survival through nutrient cycling. Decomposer activity in soil and litter beneath decayed roots created microfood webs, breaking down organic matter and releasing nutrients vital to other subterranean species. Fossilized pupae and larval cases suggest that some insect populations paused development during peak cold, resuming life only when conditions moderated. These underground ecosystems, though quiet and hidden, sustained the first threads of continuity in post-impact food webs. Burrow temperatures remain remarkably stable compared to the frozen surface, preserving juvenile development and reproductive cycles. Fossilized nests discovered within subterranean chambers indicate that early mammals timed births to coincide with localized temperature maxima rather than surface seasonality. Similarly, reptiles and amphibians likely utilized soil insulation to avoid lethal freezes, emerging only sporadically to forage or relocate. By buffering life against the extremes of climate, these underground refuges provided a sanctuary for the continuity of populations and the gradual restoration of ecological processes. Isotopic analyses of subterranean soils and bones indicate metabolic adjustments, including lowered activity and energy conservation. Small mammals display dental and skeletal patterns consistent with reduced feeding and movement, while isotopic signatures in preserved bone collagen reveal reliance on stored or opportunistically acquired food. These adaptations underscore a fundamental truth. Survival was governed not by speed or strength, but by the capacity to endure scarcity and exploit environmental niches invisible to the unprepared eye. Nest structures, both fossilized and implied through sediment patterns, show deliberate placement to maximize insulation and safety. Birds, early marsupials, and rodents appear to have chosen chamber depths, orientations, and substrate materials to buffer against frost and fluctuating humidity. The meticulous selection of nesting sites demonstrates behavioral complexity and environmental awareness, highlighting how life reorganized itself to persist under prolonged duress. Even the smallest details, a curled leaf, a compacted soil wall, or a sheltered nook, became critical for survival. Predation risk is minimized underground, yet competition for space and food drives cautious territorial behavior among surviving species. Evidence from burrow spacing and trace fossils suggests that social interactions and avoidance strategies were refined even in miniature post-impact communities. Opportunistic species might temporarily share tunnels, while others defended prime locations vigorously, revealing the delicate balance between cooperation and competition that defined early Paleocene's subterranean life. Microbial communities flourish in these hidden environments, decomposing organic matter and supporting the faint pulse of underground ecosystems. Soil analyses indicate high microbial activity beneath logs, roots, and burrow walls, providing nitrogen and other nutrients essential for insects, small mammals, and other occupants. These quiet biochemical processes, invisible to the naked eye, sustained life when above-ground food sources were scarce or toxic. The underworld, in its darkness, became the engine of continuity, a quiet crucible where life endured and adapted. The quiet darkness fosters slow but continuous ecological interaction, forming the backbone of eventual recolonization above ground. Burrows connect to decayed tree roots and small fissures, creating networks that allow gradual expansion once conditions improve. Fossil evidence suggests incremental dispersal from these refuges, with individuals venturing briefly to forage and then returning to shelter, creating a pattern of cautious but steady recovery. In this hidden realm, life persists in measured rhythms, conserving energy and maintaining populations ready to seize opportunity. When life eventually resurges from the underworld, these burrows and nests will provide the foundation for the next wave of post-impact renewal. Mammals, birds, reptiles, and insects emerge from their insulated sanctuaries, carrying with them the legacy of behavioral and physiological adaptations that allowed survival during one of Earth's darkest years. These refuges, shaped by ash, soil, and root systems, become the springboard for recolonization and evolutionary experimentation. As the frozen surface thaws and fire-scarred landscapes begin to reshape, the organisms of the underworld are poised to reconnect with the world above, demonstrating that even in the aftermath of planetary catastrophe, life finds ways to endure and expand. When fire became a season, flames crackle across a landscape scarred by cold and desolation, igniting the skeletal remains of forests that survived the winter. The blackened trunks of fallen conifers and scorched ferns create an eerie tableau, smoke curling into a dim, sunless sky. Charcoal layers preserved in Paleocene sediments reveal that these fires were not isolated events, but part of a recurring seasonal pattern, ignited by lightning strikes and fueled by accumulated, desiccated biomass. In these first post-impact years, fire became an agent of both destruction and renewal, erasing weakened vegetation while simultaneously creating new opportunities for life to reorganize and persist. Lightning strikes, splitting dry limbs, and igniting tinder left by fallen Cretaceous trees set new patterns of destruction in motion. Evidence from fossilized charred wood indicates that even isolated strikes could propagate rapidly, aided by strong winds and the accumulation of dead plant matter left from impact-driven die-offs. The resulting infernos transformed local topography, creating patchy burn zones interspersed with untouched refuges, where small mammals, reptiles, and insects could escape immediate danger. Each fire reshaped the ecological architecture, clearing space for opportunistic species to exploit post-burn microhabitats. Charcoal layers embedded in early Paleocene sediments record repeated wildfire events, revealing a world where fire became a seasonal force rather than an anomaly. Sediment cores across North and South America, Europe, and Asia indicate multiple pulses of burning within a single year, suggesting that post-impact climates, combined with dry surface conditions, facilitated fire recurrence. These layers provide a fossilized record not only of the intensity and frequency of fire, but also of its spatial heterogeneity, demonstrating how different ecosystems responded variably to thermal disturbance. Ash drifts across plains and valleys, altering soil chemistry and providing a nutrient pulse for opportunistic plants and microorganisms. Nutrient-rich sediments, particularly phosphorus and nitrogen concentrated in ash deposits, enhance soil fertility in burned patches, allowing pioneer species to sprout rapidly where competitors had been removed. Mosses, ferns, and early flowering plants exploited these nutrient-rich niches, forming the first wave of recolonization above ground. Even microbial communities in the soil shifted in composition and activity, breaking down residual organic matter and sustaining the initial recovery of the terrestrial food web. Small mammals and birds respond to smoke and heat with rapid dispersal, seeking temporary refuge in surviving hollows or burrows. Fossilized trackways and nesting evidence show that these animals exhibited remarkable mobility, moving from one safe zone to another in response to encroaching fire fronts. Burrows previously occupied for winter survival became temporary sanctuaries, while birds and small reptiles exploited vertical space in surviving trees. Opportunism became the defining behavioral trait in a world dominated by ephemeral resources and fluctuating hazards. Recolonizing vegetation sprouts first in patchy clearings, exploiting the reduced competition and enriched post-fire soils. Charcoal-stained roots show that pioneer species established themselves quickly, stabilizing the soil and preventing excessive erosion. These plants served as the foundation for incremental habitat recovery, creating food and shelter for returning insects and vertebrates. The interplay between fire, soil chemistry, and vegetation dynamics illustrates a complex feedback loop where destruction accelerates ecological innovation and adaptation. Reproductive strategies shift as survivors capitalize on ephemeral resources created by burned landscapes. Fossilized nests and burrow remains suggest that small mammals timed reproduction to coincide with post-fire flushes of vegetation and insect availability. Birds similarly established temporary nesting sites in surviving hollowed trunks, capitalizing on reduced predation and competition. These adaptations reflect a subtle but profound shift in life history strategies, emphasizing opportunistic exploitation over territorial persistence in a landscape in constant flux. Rivers and streams carry fine ash downstream, influencing sediment deposition and early aquatic recolonization patterns. Analyses of Paleocene sediment cores indicate that ash influx altered water chemistry, increased turbidity, and delivered concentrated nutrients to floodplains and coastal margins. Fish, amphibians, and invertebrates experienced both disruption and opportunity, as post-fire sediments created new habitats while carrying a chemical record of the fires themselves. The coupling of terrestrial and aquatic responses underscores the interconnectedness of ecosystems reshaped by repeated fire events. Evidence from fossil charcoal and soot layers demonstrates fire frequency and intensity, informing our understanding of post-impact ecological dynamics. Variations in charcoal particle size, depth, and composition allow paleontologists to infer flame height, burn temperature, and recurrence intervals. This evidence reveals that fire acted as a selective pressure on early Paleocene species, favoring traits such as mobility, burrowing, dietary flexibility, and reproductive opportunism. Fire was both a sculptor and a filter, shaping which species could persist and which niches would remain open for colonization. The heat, smoke, and shifting nutrient balance drive both destruction and opportunity, shaping the new biosphere with each conflagration. In some areas, fires cleared vast tracts, leaving ash-laden plains with only the hardiest species surviving. In others, partial burns created mosaics of refuge and regrowth. Fossil evidence shows that even small-scale fires catalyzed rapid ecological restructuring, accelerating evolutionary trajectories and forcing life to adapt to unpredictability. Fire, once a rare visitor, became an integral rhythm in the post-impact environment, a recurring pulse that both challenged and enabled survival. Microhabitats created by fallen, scorched trees provide shelter and foraging sites, supporting species emerging from underground refuges. Mammals, reptiles, and insects reoccupied these burned areas, exploiting the nutrients, cavities, and structural complexity left behind. These post-fire microhabitats formed transitional ecosystems where life could cautiously expand, bridging the gap between hidden underground refuges and the broader surface world. The interplay between shelter and exposure defined survival and facilitated the incremental recovery of ecosystems devastated by the asteroid impact. In the ashes of these fires, a transformed biosphere emerges, illustrating how catastrophe reshapes life and the air itself. Smoke-filled skies, nutrient-enriched soils, and scattered survivor populations demonstrate that fire, though destructive, was a central architect of early Paleocene renewal. As these burned landscapes evolve, they lay the groundwork for the next stage of planetary recovery. Subtle chemical and atmospheric shifts that ripple through terrestrial and marine ecosystems alike, revealing the far-reaching consequences of fire's sudden dominion over a recovering world. Fern world rising. Breaking through the ashen forest ground, slender fronds pierce ash-laden soil, heralding the first green resurgence since the impact. Across continents once dominated by Cretaceous giants, ferns erupt with a quiet intensity, blanketing barren landscapes with a pioneering green that signals life's stubborn persistence. Paleobotanical studies reveal thick layers of fern deposits in North America, Europe, and Asia, each layer chronicling rapid recolonization within months to a year after wildfire and impact-induced devastation. In the aftermath of fire and soil disruption, ferns exploited light gaps and nutrient pulses, creating the first major wave of post-extinction recovery visible from horizon to horizon. Swept over vast landscapes, spores drift on wind currents, settling in nutrient-rich patches left behind by repeated fires. These tiny reproductive units, abundant and resilient, allowed ferns to disperse widely, even to remote burned regions, where seed plants were slower to recover. The spores' capacity to germinate in ash-laden soil provided a remarkable advantage, outpacing slower-growing shrubs and early flowering plants struggling to establish. Fossil evidence shows that vast swaths of the Paleocene landscape were dominated by ferns, forming a contiguous green carpet that altered local microclimates and provided shelter for emerging animal life. Fossil layers reveal thick, continuous fern deposits, marking a period of global vegetative expansion unparalleled in the early Paleocene. In some North American sites, fern layers reach several meters in depth, a testament to both their reproductive efficiency and the scale of ecological opportunity created by fire and extinction. Sediment cores indicate that fern dominance lasted for decades, stabilizing soils, reducing erosion, and establishing microhabitats that would support subsequent waves of plant and animal colonization. The fern spike thus serves as a tangible record of the first planetary-scale recovery effort following one of Earth's most catastrophic events. These pioneer plants rapidly stabilize soils, prevent erosion, and create microhabitats for surviving fauna emerging from underground refuges. Insects, small mammals, and reptiles move tentatively among the fresh fronds, discovering shelter, forage, and pathways through otherwise exposed terrain. Burrows previously used to escape winter and fire now open onto verdant undergrowth, where herbivorous insects graze and omnivorous mammals forage for seeds and spores. The interaction between fern cover and returning fauna marks the beginning of a subtle ecological web, where vegetation structure directly shapes the behavior and survival of animal life. Shade-tolerant and fast-growing, ferns exploit light gaps, outcompeting other early colonizers in the barren, post-impact terrain. Their ability to photosynthesize under low-light conditions allowed them to flourish beneath clouds of lingering aerosols, while their rapid leaf turnover returned organic matter to the soil. In turn, nutrient-enriched soils facilitated further fern growth and created pockets of fertility that would be critical for seed plants attempting to establish later. Each generation of fronds expanded the green footprint, creating continuity in the landscape where patches of ash and burnt wood had once dominated. Insects and small vertebrates begin to forage among the fresh fronds, illustrating the interdependence between flora and returning fauna. Early Paleocene beetles and leaf-mining insects exploited the tender leaves, while small reptiles hunted insects sheltering within the fern cover. Fossilized insect feeding marks on fronds indicate that even in the wake of catastrophic extinction, ecological interactions re-emerged rapidly, bridging the gap between plant colonization and animal behavioral adaptation. The fern spike thus represents not only vegetative recovery, but also the re-establishment of ecological processes fundamental to the rebuilding of complex ecosystems. The fern spike acts as a biological signal, revealing areas where fire, ash, and soil chemistry converge to permit rapid regeneration. Charcoal layers beneath the fern mats document prior burn events, linking vegetation patterns to fire history and nutrient enrichment. In regions where fires were less intense or soils retained more moisture, fern proliferation was patchy, illustrating how landscape heterogeneity guided the pace and distribution of recovery. By analyzing these patterns, paleobotanists can reconstruct the spatial choreography of post-impact recolonization and the interplay between disturbance and renewal. Layers preserved in sediment cores reveal that fern dominance persists for decades, offering insight into the pace and trajectory of post-extinction succession. Isotopic analyses of carbon and nitrogen suggest that the rapid spread of ferns influenced soil chemistry and nutrient cycling, affecting subsequent plant communities. Ferns also played a role in stabilizing early food webs. Herbivorous insects fed on abundant foliage, which in turn supported small vertebrates, establishing a renewed ecological foundation. The fern spike, therefore, was more than a botanical event. It was a keystone in the reconstruction of terrestrial life. Reproductive strategies of ferns including massive spore output and wind dispersal, allow colonization of far-flung burned landscapes. Unlike seed plants, ferns could reproduce in large numbers without reliance on animal pollinators, giving them a competitive advantage in a depopulated world. This reproductive efficiency enabled the first continental-scale green recovery, ensuring that even distant areas affected by fires or impact events would eventually receive pioneering vegetation. The global consistency of fern spikes in fossil records highlights the remarkable speed and scale of this ecological phenomenon. Early Paleocene birds and small mammals take advantage of the protective cover provided by dense fern thickets, feeding and nesting in these temporary shelters. Fossilized burrows and nest sites indicate that animals adapted quickly to the new vegetative structures, exploiting both protection from predators and access to food. Fern mats acted as living refuges, bridging the gap between subterranean survival strategies and life above ground, and facilitating the gradual re-establishment of more complex terrestrial ecosystems. The interplay between fern proliferation and residual soil nutrients illustrates a feedback loop that accelerates the stabilization of ecosystems. As ferns grew and decomposed, they returned essential elements to the soil, preparing the ground for later colonizers. Microbial communities thrived on this organic input, further enhancing soil fertility and supporting successive generations of vegetation. Together, plants, animals, and microbes coalesced into a fragile yet resilient network, signaling the first steps of long-term planetary recovery. Above these reborn plains, the skies hold their own dramas as the atmosphere slowly recovers, carrying spores, ash remnants, and the promise of the next wave of ecological complexity. The fern spike, vivid and global, is a testament to life's ability to rebound after devastation. But it also serves as a reminder that recovery is measured in stages, each dependent on the subtle interplay of climate, soil, and surviving organisms. As green mats spread across continents, the planet begins to breathe again, setting the stage for subsequent waves of plant diversification, animal resurgence, and the intricate choreography of a recovering Earth. Skies clearing, worlds dividing. Through the drifting haze above the plains, thin shafts of sunlight begin to pierce, revealing the contours of a recovering world. The fern-dominated landscapes, once muted under a dim, ash-laden sky, now catch flecks of golden illumination, casting long, intricate shadows across the still recovering terrain. Atmospheric measurements inferred from isotopic studies suggest that while a substantial fraction of post-impact aerosols had settled within a year, concentrations remained high enough to produce patchy light and uneven warming across continents. Satellite analogues derived from sedimentary deposits show that the first regional weather systems were forming, driven by the uneven heating of land masses and ocean surfaces, creating pockets of warmth and cold that would dictate which organisms survived and which faltered. Winds sweep across continents, carrying residual ash, microscopic spores, and the earliest hints of regionally differentiated weather patterns. Paleoclimate reconstructions indicate that mid-latitude areas experienced highly variable winds and intermittent storms, a stark contrast to the relatively stable conditions beneath the dense fern mats of lowlands. These currents transported nutrients and propagules across hundreds of kilometers, seeding both terrestrial and nearshore ecosystems. In effect, the atmosphere became a conveyor belt, linking burned plains, recovering forests, and nascent rivers, delivering not just material but also the climatic pressures that would sort survivors from casualties. Temperature gradients emerge as aerosols gradually settle, revealing early Paleocene thermal contrasts. Northern and southern hemispheres exhibit divergent warming rates, with some equatorial regions experiencing brief heat surges, while higher latitudes remain locked in cold, grey light. Isotopic analysis of fossilized plant matter indicates that growth rates fluctuated dramatically according to these thermal pockets, producing pronounced variations in leaf morphology and stem density. This uneven heating created microclimates that dictated both plant productivity and animal movement, defining the boundaries of survival in a world still recovering from planetary catastrophe. Evidence from sediment and ice core analyses shows that rainfall became sporadic and unpredictable, a phenomenon mirrored in the depositional record of early Paleocene rivers. Areas once teeming with steady freshwater flow now exhibit evidence of intermittent floods, flash runoff, and sediment-choked channels, all reflecting the turbulence of a sky still clearing from impact-induced aerosols. These hydrological irregularities dictated which fern mats, shrubs, and early flowering plants could persist and which were swept away, illustrating how atmospheric recovery directly influenced terrestrial ecosystem stability. Storm systems, though chaotic, began carving the emerging contours of ecological opportunity. Lightning ignited occasional fires in dry patches, while localized downpours nourished other regions, creating a dynamic mosaic of destruction and renewal. Fossil charcoal layers interbedded with fern mats indicate repeated small-scale fires, each event redistributing nutrients, creating gaps for colonization, and further altering microclimatic conditions. These early storm patterns, unpredictable as they were, reinforce the interplay between recovery, destruction, and selective pressure on surviving organisms. Sunlight penetration, gradually increasing, catalyzed photosynthetic activity across the fern, plains, and nascent herbaceous communities. Measurements from leaf fossils suggest elevated chlorophyll deposition and accelerated growth in areas receiving consistent light, while shaded regions lag, reflecting the uneven distribution of solar energy. This solar-driven productivity provided the energy foundation for small mammals, insects, and reptiles emerging from burrows and nests, linking atmospheric clearing directly to terrestrial ecological resurgence. Atmospheric chemistry shifted in tandem with these visible changes. Sulfate aerosols and fine particulate matter diminished, increasing the ratio of oxygen to carbon dioxide in localized pockets. Early Paleocene isotopic data indicate that these chemical shifts allowed oxygen levels to rebound slowly, enhancing the survivability of warm-blooded species while facilitating the slow expansion of primary producers. The clearing sky thus represented both a literal and symbolic lifting of constraints, setting the stage for complex interactions among plants, animals, and microbial communities. Regional climate contrasts further shaped ecological outcomes, effectively dividing the world into zones of opportunity and stagnation. Some areas, benefiting from consistent sunlight and moderate precipitation, saw rapid growth of vegetation, while others remained subdued under residual haze or erratic rainfall. This uneven distribution fostered pockets of rich biodiversity where survivors could thrive, while inhospitable zones acted as crucibles, testing the adaptability of organisms forced to cope with unstable conditions. In this way, the clearing skies created a world of winners and losers, of resilience measured against environmental unpredictability. Faunal behavior responded quickly to these new atmospheric dynamics. Small mammals foraged during brief warm intervals, insects emerged to exploit plant resources, and birds navigated shifting winds to reach favorable feeding grounds. Evidence from burrows and fossil tracks indicates that animals adjusted activity patterns according to light, temperature, and rainfall, reflecting an acute sensitivity to the atmosphere's ongoing transformation. The first signs of adaptive behavior, tied directly to climate variability, highlight the interplay between environmental change and evolutionary pressures. Fossilized plant growth rings provide additional insight into this delicate balancing act. Rapid growth in areas receiving consistent sunlight contrasts sharply with stunted growth in shaded or windswept regions, reinforcing the narrative of atmosphere-driven ecological sorting. By analyzing these patterns, paleobotanists can reconstruct not just plant resilience, but also the emerging distribution of animal populations, creating a multidimensional portrait of early Paleocene survival in a clearing but still unstable world. Bathed in the morning glow, plants take their first bold step toward rebuilding Earth's oxygen engines, marking the beginning of a critical stage in planetary recovery. The interplay of light, heat, precipitation, and atmospheric chemistry drives the expansion of photosynthetic capacity, the stabilization of food webs, and the gradual re-establishment of functional ecosystems. These early successes are fragile, dictated by the whims of weather and geography, yet they illuminate a path forward, from a planet shrouded in gloom to one where green life thrives, oxygen rises, and ecological complexity slowly reasserts itself. Above these plains, the atmosphere is no longer uniform. It is fractured, dynamic, and alive, shaping the rhythms and opportunities for the first global resurgence of plant productivity and the creatures that will depend on it. The forests attempt to breathe again. In the quiet under the fractured skies, the first shoots of angiosperms pierce ash-enriched soil, a fragile promise of renewal. Tiny leaves, glistening with dew, emerge through layers of post-impact detritus, exploiting patches of light that filter through lingering haze. Fossilized growth rings indicate accelerated cell division, a response to the brief but critical periods of sunlight, while isotopic studies of carbon reveal these early plants were already contributing measurably to atmospheric oxygen. Each new sprout, delicate yet persistent, represents the planet's tentative reclaiming of life, pushing upward from the soil that had spent months in near stasis. Conifers, once overshadowed by Cretaceous giants, stake their claim in open patches, their needles stabilizing soil and shaping microclimates. Paleobotanical evidence shows species such as Picea and Pinus pioneers rapidly expanded into burned plains, their resin-rich tissues deterring herbivory and fostering localized nutrient retention. Roots penetrate ash and sediment, binding loose substrates and moderating the effects of intermittent rainfall, while the vertical architecture of these emerging forests begins to create shade gradients that influence the next generation of seedlings. In combination with angiosperm colonizers, conifers establish the earliest functional canopies, subtle yet profound in their ecological impact. Leaf fossils reveal subtle adaptations, thicker cuticles, rapid growth rates, and drought-resistant structures suited to lingering post-impact stress. Paleoclimatic reconstructions indicate that even a year after the impact, areas of high light exposure alternated with dim, aerosol-shrouded zones, driving evolutionary pressure toward flexible, photosynthetic strategies. Plants with these traits outcompeted slower-growing species, ensuring that early forests were composed of organisms capable of surviving the twin challenges of cold and intermittent light. This selective filtering laid the foundation for plant communities that would persist and diversify in the millennia to come. Root networks intertwine beneath the surface, beginning the slow reconstruction of soil architecture disrupted by fire, wind, and flood. Microbial mats, symbiotic fungi, and decomposing plant matter coalesce to form a complex, living soil capable of retaining nutrients and moisture. Analysis of fossilized root traces demonstrates how subterranean structures redistributed mineral content, enabling subsequent seedlings to establish more rapidly than their predecessors. These underground dynamics were invisible from above, yet they dictated which forests would flourish and which would falter in the fragile post-impact landscape. Shadows of fallen trees create pockets of shade, enabling shade-tolerant species to germinate while sheltering small animal survivors. Burrowed mammals, early birds, and insects exploit these microhabitats, feeding on decaying organic matter and newly sprouted vegetation. Evidence from fossilized leaf litter and coprolites suggests that these interactions were already shaping nutrient flow and species distributions, a quiet but critical step toward ecosystem stability. In this way, the forests themselves became architects of life, structuring both flora and fauna through patterns of light and shade. Fern mats persist alongside seedlings, forming layered vegetation that buffers temperature extremes and retains moisture. Palynological studies confirm that ferns continued to dominate open spaces, their spores aiding in soil stabilization and providing a temporary canopy for more vulnerable seedlings. By creating pockets of microclimate stability, these ferns facilitated survival for both plants and small animals, acting as an intermediary stage between total collapse and full forest regeneration. The interplay between ancient ferns and emerging angiosperms underscores the layered complexity of early Paleocene recovery. Pollen records indicate that flowering plants quickly colonized areas cleared by fire, setting the stage for diverse floral assemblages. Rapid dispersal through wind and surviving pollinators enabled angiosperms to exploit nutrient-rich open patches created by wildfire and erosion. Fossilized pollen grains show variation in size, shape, and dispersal strategy, reflecting adaptation to a landscape where light, moisture, and soil quality varied unpredictably. This early experimentation in colonization would ultimately drive the incredible diversification of flowering plants over the following millions of years. Microclimatic variation fosters distinct plant communities, some thriving in nutrient-rich patches, others constrained to thin, rocky soils. Analyses of sediment layers indicate that forest composition varied not just across continents, but within tens of meters, as slight differences in soil depth, moisture retention, and microtopography dictated which species could take root. This heterogeneity created the first patches of complex, spatially differentiated ecosystems, a precursor to the modern forest mosaics seen today. Interactions between roots, fungi, and microbial communities accelerate nutrient cycling, quietly reconstructing the ecosystem's metabolic foundation. Soil chemistry analyses reveal elevated nitrogen and phosphorus availability in areas where fungal hyphae and plant roots formed early symbioses. These nutrient surges enhance growth rates for angiosperms and conifers alike, while supporting the first waves of insect herbivores and detritivores. By establishing subterranean networks of life, the forests created conditions for resilience, enabling both plants and animals to survive in a post-catastrophe world. Early herbaceous growth attracts insects and small mammals, establishing the preliminary links of emerging food webs. Fossilized trackways, burrows, and coprolites reveal that even at this nascent stage, herbivory, pollination, and seed dispersal networks were beginning to take shape. These interactions, subtle yet essential, connected the regenerating forests to broader ecological systems, reinforcing the idea that recovery was not just a vertical growth of plants, but a complex web of interdependent life. Canopy shadows lengthen as seedlings mature, illustrating the delicate choreography between vertical growth and ecological competition. Gradually, forest structure begins to resemble recognizable patterns. Understory plants exploit light gaps, mid-canopy shrubs expand, and emergent conifers tower over the developing landscape. Fossilized stems and leaf layers suggest that within a year, some areas achieved notable stratification, hinting at the long-term potential for diverse habitats capable of supporting richer faunal communities. As vegetation returns, herbivores follow, and with them, the first tentative stirrings of new food webs begin to take shape, linking the renewed forests to the broader ecosystem. Small mammals forage amidst seedlings, insects exploit both foliage and detritus, and birds test flight within sheltered canopies. These early interactions are fragile, dictated by light, temperature, and resource availability. Yet they signal the first functional networks of the post-impact Earth. In observing these tentative beginnings, one can imagine the cascading ecological complexity yet to unfold as forests continue to knit themselves together, establishing the framework for future terrestrial dominance. The first new herbivores. Sprouting greenery invites cautious foragers to explore its fragile bounty, as small mammals, early birds, and turtles tentatively reclaim ecological niches once dominated by towering dinosaurs. Fossil evidence from early Paleocene sites shows that multituberculates and other tiny mammals ventured from their burrows to sample shoots, seeds, and spores, exploiting gaps left by mass extinction. Each bite, each gnawed stem, contributed not only to survival, but also to shaping the regenerating plant communities. The delicate balance of light, temperature, and nutrient availability dictated where these pioneers could thrive, with some species showing remarkable flexibility in exploiting microhabitats that remained protected from harsh sunlight or persistent cold. Tiny mammals probe leaf litter with dexterous paws and specialized teeth, consuming both vegetation and the detritus that fuels soil nutrient cycling. Fossilized jaw and tooth structures reveal adaptations for gnawing soft shoots, spores, seeds, and fungal matter, indicating a diverse diet tailored to the early Paleocene landscape. Observations suggest that species like Purgatorius and other small insectivorous or omnivorous mammals were already partitioning resources, reducing direct competition while supporting decomposer populations. These subtle interactions, largely invisible in the fossil record, were critical in stabilizing nutrient flows within recovering forests, linking flora and fauna in the earliest post-impact food webs. Embedded in fossilized jaw structures are clues to precise dietary adaptations, illustrating how each species navigated the limitations of post-extinction ecosystems. Seed-crushing teeth, blade-like incisors, and molars adapted to fibrous plant material demonstrate evolutionary responses to both available vegetation and predation pressure. Early birds, such as Asterionis, combined insectivory with opportunistic herbivory, skimming over canopies and probing leaf litter for invertebrates disturbed by mammalian foraging. These behaviors not only expanded the spatial reach of energy transfer, but also facilitated early pollination and seed dispersal networks, setting the stage for plant diversification across recovering landscapes. Early birds skim across canopy gaps, harvesting insects stirred by herbivore activity below, while demonstrating agile navigation through partially regrown forests. Feather impressions preserved in fossilized sediments indicate adaptations for maneuverability in cluttered understory environments, suggesting that even a year after impact, avian life was beginning to exploit vertical forest strata. These small aerial foragers complemented terrestrial herbivores, reinforcing food web interactions that relied on movement, predation, and opportunistic feeding. The dynamics of bird-mammal interaction, though subtle, exemplify the intricate ecological relationships forming at the dawn of a new biosphere. Shell-bearing turtles navigate shallow wetlands, grazing on tender aquatic plants and detritus while avoiding predators and desiccation. Fossilized carapace morphology indicates adaptations to fluctuating water levels and variable sedimentation caused by post-impact floods and debris flows. These reptiles played a dual role. As consumers, they processed plant and algal matter, and as dispersers, they carried seeds and spores across fragmented aquatic systems. Their presence underlines the importance of semi-aquatic niches in stabilizing emerging food webs and maintaining connectivity between terrestrial and freshwater ecosystems. Seasonal variations challenge these pioneers, forcing flexibility in feeding, movement, and reproductive timing. Isotopic analysis of teeth and bones suggests that early mammals and reptiles experienced truncated growing seasons, altered by dim sunlight and cooler temperatures, yet adjusted their behaviors to optimize energy intake. Some mammals burrowed more extensively, while birds modified flight and foraging schedules, reflecting resilience in the face of environmental uncertainty. These behavioral adaptations were crucial to survival, allowing species to persist long enough for forests and wetlands to stabilize around them. Footprints preserved across millennia revealed daily rhythms of foraging and predator avoidance, providing insight into the early structuring of ecosystems. Footprints of multituberculates, small marsupial relatives, and hatchling birds preserved in mud layers indicate synchronized activity patterns, suggesting an awareness of risk and resource availability. Such spatial and temporal partitioning reduced direct competition, ensuring that multiple species could coexist even in resource-limited environments. These patterns laid the groundwork for increasingly complex interactions as populations expanded and forest density increased. Root zones and decomposing wood provide both food and protection for small vertebrates, highlighting the interplay between plant and animal communities. Burrowing mammals exploit the soft, nutrient-rich substrate beneath fallen trees, while insects accelerate decay and soil aeration. Fossilized nests and burrows demonstrate that mammals and birds were already leveraging these microhabitats for shelter and reproduction, contributing to the spatial heterogeneity that defines modern forests. By occupying these protective niches, herbivores stabilized early forest regeneration while simultaneously shaping the very soil they depended upon. Insect-herbivore interactions create micro-food webs that shape plant community composition, demonstrating how small creatures exert outsized influence on recovery trajectories. Beetles, caterpillars, and leaf-mining larvae feed on newly sprouted leaves, while mammalian foraging disperses plant material and seeds. Coprolite evidence confirms that nutrient recycling was active even at this early stage, supporting both plant growth and detritivore populations. These interactions underscore the subtle yet profound mechanisms that allow ecosystems to rebuild from near total collapse. Nesting behaviors indicate early reproductive strategies, synchronized with resource availability, ensuring survival despite environmental volatility. Fossilized eggshell fragments and burrow impressions suggest that some mammals timed birth cycles to coincide with the availability of edible shoots and insect surges, while birds adapted nesting heights and structures to balance protection and foraging efficiency. These reproductive adaptations highlight a critical evolutionary response to post-impact pressures, enabling populations to maintain continuity and gradually expand in a recovering landscape. Spatial segregation within forests reduces competition and allows the coexistence of multiple species, each occupying specific microhabitats. Fossil evidence shows mammals foraging along leaf litter, turtles grazing aquatic margins, and birds navigating canopy gaps without direct overlap, effectively partitioning resources. This subtle structuring of space and behavior created the first stable, multi-species networks that could sustain increasing biodiversity, hinting at the eventual re-emergence of more complex ecosystems. Wandering the newly reborn forests, herbivores spread, their presence silently calling forth the next wave of predators, shaping the trajectory of post-impact evolution. Small mammals, birds, and turtles create the necessary conditions for carnivorous species to re-establish, defining trophic hierarchies that will dominate for millions of years. The tentative foraging, nesting, and dispersal of these pioneering herbivores mark the first functional food webs of the Paleocene, demonstrating that even after Earth's most catastrophic extinction, life continues to adapt, occupy niches, and prepare the stage for the predators that will inevitably follow. Predators without precedent. Slipping through the nascent forests, predators patrol territories defined as much by opportunity as by instinct. In a world bereft of towering dinosaurs, early mammals, snakes, and flighted birds exploit niches that have lain dormant for millions of years, their movements deliberate, calculating, and precise. Fossil evidence from teeth, claws, and limb bones reveals a startling versatility. Small mammals capable of rapid bursts of speed navigate fallen logs and dense undergrowth, while arboreal birds dart between budding canopies, snatching insects or the occasional juvenile reptile. Even snakes, often hidden within the litter and hollows, slither into carnivorous prominence, ambushing prey with stealth and lethal efficiency. Their emergence underscores a radical reorganization of trophic hierarchies, demonstrating that the absence of giants created an evolutionary vacuum filled by the adaptable and opportunistic. Dentition and jaw mechanics illustrate an adaptive ingenuity unseen in pre-impact ecosystems. Some small mammals exhibit dentary features optimized for shearing tough plant matter, but repurposed for insectivory or opportunistic carnivory in the post-impact environment. Early multituberculates, for instance, showcase molar patterns capable of crushing both seeds and arthropods, highlighting dietary plasticity. Similarly, birds with hooked beaks and sharp talons exploit prey otherwise inaccessible, their flight patterns honed to the fragmented forest landscape. Coprolites' fossilized excrement revealed diets astonishingly diverse for creatures of their size, including insects, amphibians, small reptiles, and juvenile mammals, suggesting that dietary versatility was a survival imperative in these fragile ecosystems. Territorial confrontations among emerging predators indicate the early establishment of hierarchies and competitive behaviors. Fossilized bite marks on contemporaneous mammal bones point to intraspecific skirmishes, while skeletal evidence of muscle attachment sites implies bursts of speed, climbing prowess, and predatory dexterity. Nocturnality appears widespread, inferred from orbital morphology and comparisons to modern analogues, suggesting that hunting under the cover of darkness minimized risk from competitors and maximized access to prey. Even subtle behavioral traits, such as burrow raiding or nest predation, leave traces in the fossil record, painting a vivid picture of predation tactics adapted to a world without former apex predators. Environmental constraints shape the strategies and success rates of these fledgling predators. Patchy vegetation, isolated water sources, and lingering ash deposits create a landscape of microhabitats where opportunistic hunting, burrow ambushes, and scavenging become central survival tactics. Predators demonstrate remarkable flexibility, exploiting both terrestrial and arboreal zones, shifting diet with seasonal availability, and navigating terrain that remains unstable from post-impact upheaval. Microtopography, from fallen tree trunks to volcanic ash layers, creates refuges for prey, but also hunting corridors for predators, emphasizing the codependence of terrain and trophic behavior in early Paleocene ecosystems. Fossil trackways, preserved in fine-grained sediments near river margins, capture fleeting glimpses of predatory behavior. Small mammals sprinting across open patches, birds hopping and flitting in pursuit of insects, and snakes coiling through leaf litter. These ephemeral traces illustrate coordinated movement, avoidance strategies, and the first functional post-extinction food webs, offering a dynamic view of ecosystems slowly rebuilding under selective pressures. Even minor variations in stride, claw marks, and footprint spacing provide insights into speed, hunting tactics, and territorial boundaries, revealing a level of ecological complexity that belies the diminutive size of these predators. Microevolutionary responses unfold rapidly within these early predator populations. Variations in jaw strength, limb proportion, and claw morphology reveal localized adaptations to prey availability, habitat structure, and competition intensity. Even within a single genus of early mammal, subtle differences in size and mobility suggest that natural selection was accelerating the diversification of carnivorous strategies. Birds, too, display evidence of rapid adaptive radiation, with wing shape, claw curvature, and beak specialization reflecting an early partitioning of ecological roles that will define their descendants for millions of years. Morphological plasticity is further enhanced by environmental fluctuations, highlighting how these pioneering predators continually adapt to a recovering but unstable world. Behavioral innovation complements anatomical adaptation. Some mammals demonstrate caching behavior, storing insects or seeds for lean periods. Snakes use ambush positions near riverbanks to capture amphibians emerging from shallow pools. And raptor-like birds employ cooperative hunting or gliding tactics to conserve energy. This combination of learned and inherited strategies accelerates the establishment of functional trophic networks, shaping the flow of energy through ecosystems and directly influencing the survival of prey populations. With dominance rising among these emergent predators, they begin to mold the ecosystems themselves, influencing herbivore behavior, plant distribution, and the microhabitats of smaller organisms. The presence of hunters imposes a new rhythm on the forest floor and canopy, dictating feeding schedules, migration patterns, and reproductive timing for prey species. Even in the absence of giants, life is no longer passive. It responds, adapts, and negotiates the newly drawn rules of survival. Predators without precedent, though small in stature, are powerful architects of post-impact ecological structure, shaping landscapes in ways both visible and subtle. The forests, once tentative and fragile, have become arenas of tension and opportunity. Small Paleocene predators, though diminutive compared to the dinosaurs that came before, assert an outsized influence, shaping food webs, guiding the movements of herbivores, and setting in motion the subtle ecological feedback loops that will ripple through the recovering landscapes. Life exploits the spaces left vacant by catastrophe, seizing openings with ingenuity and persistence, quietly redefining the forest floor and canopy in ways both immediate and enduring. Climbing the ecological ladder, these small predators remain shaped by the transformed continents and the lasting marks of impact, guiding their movements, concentrating their prey, and delineating their territories. From this intricate interplay of predator, prey, and environment, the story of post-impact recovery moves beyond survival into a narrative of innovation, strategy, and ecological orchestration, compelling us to witness how life, even without its former giants, relentlessly fills the spaces carved by catastrophe. The stage is now set for the final reflections on adaptive resilience and the emergent complexities of early Paleocene ecosystems, a planet becoming something new. Shattered continents reveal landscapes unrecognizable from their former selves. Impact scars, craters, fissures, and layers of ejecta stretch across plains and highlands alike, forming a terrain simultaneously alien and familiar. Ash blankets valleys, but thin streaks of light illuminate shoots of green that push upward, asserting life's persistence. These features, while harsh, define the structure through which the next generation of organisms must navigate, offering both barriers and opportunities. Across these fractured landscapes, life begins to explore, reassemble, and reclaim the spaces once dominated by giants. Sediment-laden rivers snake through valleys, carved anew by fire and impact. Their channels shift unpredictably, influenced by erosion, rainfall, and the accumulation of debris from collapsed forests. Where once clear streams flowed steadily, now torrents of ash, sand, and nutrients swirl in irregular patterns. Microbial communities, spores, and seeds travel along these currents, creating pockets of early recolonization in soils and floodplains. These waterways act as both conveyors of devastation and vectors of renewal, linking terrestrial upheaval with emergent ecological potential. Winds sweep across plains scarred by ash, redirecting rain into unpredictable patterns. Atmospheric circulation, once dominated by seasonal predictability, now carries particulate clouds that scatter sunlight unevenly across the continents. Shadows and illuminated patches alternate, influencing where pioneer plants can establish and where small animals forage. The combination of light, moisture, and temperature becomes a patchwork that challenges survival while promoting rapid evolutionary experimentation. Life responds with subtle adjustments. Shifts in foraging patterns, nesting sites, and migration routes hint at a world slowly regaining rhythm. Mammals forage cautiously among emerging seedlings, probing spaces abandoned by giants. Tiny herbivores, previously constrained to refuges, now roam open patches where angiosperms and ferns have taken hold. Nesting birds follow, gleaning insects from both soil and vegetation. Even reptiles, long overshadowed by larger predators, exploit the new light and warmth, inhabiting microhabitats left vacant. Each interaction is a delicate negotiation with risk and reward, gradually weaving the first functional networks of post-impact terrestrial ecosystems. Coastal deltas collect the chemical fingerprints of a year of upheaval. Rivers deliver sediment, ash, and nutrients to shallow seas, creating concentrated zones of biological activity. Here, small fish, invertebrates, and microbial mats exploit enriched waters, establishing the early stages of marine recolonization. Though conditions remain volatile, these deltas serve as incubators for experimentation, where life tests strategies for growth, reproduction, and survival. The interplay of land and sea, sediment and organism, becomes the blueprint for a planet-wide recovery. Currents swirl with debris and nutrients, quietly fostering the first signs of marine renewal. Algal blooms, once catastrophic, begin to settle into cycles as chemical composition stabilizes. Opportunistic species colonize the newly hospitable waters, forming patchy, provisional food webs. These ephemeral networks hint at the mechanisms by which ecosystems reconfigure themselves after global perturbation. The oceans, though still marked by loss, are a laboratory for life's ingenuity, responding to terrestrial cues while preparing the stage for future diversification. Charred soils begin to regain fertility, supporting fragile shoots that hint at recovery. Nitrogen-fixing bacteria, decomposing plant matter, and the gradual weathering of minerals enrich substrates, allowing early angiosperms and conifers to root and flourish. Pioneer plants, while individually small, collectively stabilize soils and modify microclimates, creating shelter and resources for animals. The slow accumulation of organic matter marks the first tangible return of terrestrial productivity, linking microscopic processes with landscape-scale change. Migratory paths are redrawn as surviving animals navigate fragmented habitats. Routes that once relied on continuous forest corridors are replaced by stepping stones of vegetation and refuge. Small mammals, birds, and reptiles adjust instinctively, testing distances, food availability, and predator presence. Each movement reinforces or reshapes ecological boundaries, gradually producing new patterns of distribution. In this process, the first rules of Paleocene ecology emerge, defined by opportunity, constraint, and adaptability. Small reptiles and amphibians exploit niches overlooked by larger survivors, demonstrating adaptive precision. Hidden in leaf litter, shallow burrows, or damp hollows, they forage with calculated efficiency. Their reproductive strategies, from rapid egg-laying to opportunistic feeding, allow populations to persist despite instability. By filling these marginal spaces, these creatures maintain ecosystem continuity, supporting the trophic framework that will later sustain larger herbivores and predators. Their quiet persistence illustrates the subtle but critical contributions of the smallest actors in post-catastrophe worlds. Pockets of sunlight break through lingering haze, warming patches of early regrowth. Where light touches ash-laden soils, photosynthesis accelerates, driving the first true signs of energy flow through the recovering biosphere. Seedlings stretch, insects emerge, and microorganisms metabolize newly available resources, forming a lattice of interactions, both visible and hidden. Life capitalizes on these ephemeral opportunities, demonstrating resilience at every scale. The sun, though partially veiled, becomes a central protagonist in the narrative of recovery. Erosion reshapes cliffs and floodplains, redefining ecological boundaries in subtle yet lasting ways. Channels carve deeper, deposits shift, and the contours of land itself transform. Each change affects water availability, soil composition, and vegetation patterns, compelling organisms to constantly adapt. Over months and years, these geomorphic processes not only sculpt the physical world, but also influence species distributions and ecosystem interactions. Survival is thus as much a response to the shifting land as it is to other organisms. Life seizes every opportunity offered by a world simultaneously hostile and open, hinting at the dawn of the age of mammals. The first small herbivores, predators, and pioneer plants collectively begin to stabilize ecosystems, creating interconnected networks that were unthinkable a year prior. The interplay of climate, geography, and species behavior fosters the initial web of complexity that will define the early Paleocene. From this foundation emerges the narrative of innovation, adaptation, and incremental ecological mastery. Across the transformed continents, a new chapter in Earth's story quietly unfolds, shaped not by what was lost, but by the enduring capacity of life to remake itself. A year after the dinosaurs vanished, Earth reveals both fragility and tenacity. A world reshaped by catastrophe, yet quietly insisting on life's return. In ash-choked forests, silent rivers, and murky seas, we witness survival measured in whispers and small movements, the delicate persistence of creatures too often overlooked. This is a planet learning to breathe again, where absence shapes opportunity and loss cultivates resilience. From the tiniest burrow to the first shoots of green, the Paleocene emerges, not in spectacle, but in the patient, relentless rhythm of life reclaiming the world. If you'd like to continue exploring Earth's deep history, like, subscribe, and share your thoughts below.